How do magnetic stripes prove seafloor spreading on Earth? Imagine looking at a map of the ocean floor and noticing strange, repeating patterns of dark and light bands stretching out from underwater mountain ranges. These patterns are more than just pretty lines. They tell a story about how our planet's crust is constantly moving. Scientists discovered these magnetic stripes while studying the ocean floor, and they became key evidence for understanding how the Earth's surface changes over time. During World War II, scientists used magnetometers to find enemy submarines by detecting magnetic fields underwater. These instruments, towed behind ships, measured magnetic signals from the seafloor. What they found was surprising. The ocean floor had alternating bands of normal and reversed magnetic polarity. These bands were symmetrical on both sides of mid-ocean ridges, which are underwater mountain chains that run through all the world's oceans. This pattern was not random but repeated, like a mirror image. Now, to understand why these stripes matter, think about what happens at a mid-ocean ridge. Hot magma from deep inside the Earth rises up and cools as it hits the cold ocean water. When it cools, minerals in the rock, especially magnetite, align with Earth's magnetic field at that moment. This alignment gets locked into the rock as it solidifies, creating a permanent record of the magnetic field. This process is called thermoremanent magnetization. Earth's magnetic field has reversed many times in history. Sometimes the magnetic North Pole becomes the South Pole, and vice versa. When these reversals happen, new magma that forms at the ridge records the reversed magnetic direction. As more magma erupts and cools, it creates new stripes with opposite polarity. Over millions of years, this process creates a series of alternating magnetic bands on both sides of the ridge. The symmetry of these stripes is the strongest proof of seafloor spreading. On one side of the ridge, the pattern of magnetic stripes is a mirror image of the other side. If the seafloor was not moving, these patterns would be different or random. But because they are symmetrical, it shows that new crust is constantly forming at the ridge and then moving outward in both directions. It's like two conveyor belts pushing the seafloor away from the center. Scientists also measured the age of rocks at different distances from the ridge. Rocks closest to the ridge are the youngest, and rocks farther away are older. The oldest rocks found are about 200 million years old, which fits with the idea that the seafloor is always being created and destroyed. If the ocean floor was permanent, we would find much older rocks, but the pattern shows it is continually renewing itself. When scientists compared actual magnetic data from the ocean floor with calculations based on known magnetic reversals over the past for million years, the match was perfect. The real measurements lined up almost exactly with the predictions. This confirmed that the magnetic stripes were caused by seafloor spreading, with new crust forming at mid-ocean ridges and moving outward. Heat flow data also supports this idea. The areas at mid-ocean ridges have much higher heat flow than other parts of the ocean floor. This is because hot magma is constantly rising and pushing through the crust. The seismic waves in these regions also move slower, indicating the rocks are hotter and more fractured from the upwelling magma. All these clues fit together like pieces of a puzzle, showing that the Earth's crust is always changing. The magnetic stripes also explain how continents move. Since the seafloor is spreading, the continents sitting on top of these plates are drifting apart. The stripes act like a timeline, showing when the magnetic field reversed and how fast the seafloor has moved. By counting the stripes and knowing how often the magnetic poles flip, scientists can estimate how quickly the plates are shifting. This discovery changed how scientists understand our planet. Before the magnetic stripe evidence, many thought continents and oceans were fixed in place. Now, we know Earth's crust is in constant motion, with new seafloor forming and old seafloor disappearing. Magnetometers continue to map the ocean floor, confirming that our planet's surface is always changing, slowly but surely.